Alright, good evening, guys. Welcome to today's class.
Good evening, guys. Welcome to today's class. Good evening, guys.
Alright, the topic before us today is thermal expansivity. That's the topic that we're looking at today. As you can see on the screen, what we have on the screen is the theoretical background of the topic. And like I said yesterday, during this class, we are going to be looking at a revision of WAEC, NECO, and UTME questions. But we're going to be considering the topics that we've treated right from SS1. So all classes will benefit from this class. SS1 will also benefit, for SS2 will benefit, because the topic we are considering today is from SS1 scheme. So before we go to calculation purely, let's quickly consider the theoretical background of this topic, thermal expansion. We're going to look at solid expansion, and in an exam like WAEC or NECO, you may be asked to state advantages of expansion and also the disadvantages of expansion. We will be asked to do some calculations that is related to expansivity. Okay, that's the background. So let's quickly consider solid expansion, that is expansion in solid. And with that, we are going to look at few calculations and how do we go about them. Okay, now under this thermal expansivity, we have some terms. We have terms such as linear expansivity, we have area expansivity, and volume expansivity. And for linear expansivity of a substance is defined as the increase in length per unit length per degree rise in temperature of that substance or of that object. And linear expansivity is common to objects like a rod or a bar. That is when expansion occurs in just one dimension. That is when we refer to it as linear expansion. And coefficient of that expansion is what we're looking at here as linear expansivity. And as you can see on our screen, you can see the formula for linear expansivity. Linear expansivity symbol is alpha, as you can see here, and linear expansivity is equal to this formula here. That is, you will agree with me that when expansion occurs, the size of the body in question increase. So if L1 is the initial length, when you apply it on that body, you have a new length which is referred to as L2. So the difference between L1 and L2 is what we call expansion, or you call it increase in length, that is delta L. And to calculate the coefficient of this expansion, which we refer to as linear expansivity, we make use of this formula, that is new length minus original length divided by original length multiplied by change in temperature. Change in temperature occurs when you apply it on a body. the temperature will rise from one value to another. Okay, from the formula you are seeing here, any of the parameter may be asked for in a question. That's why we try to make some of the subject of the formula. Like you can see here, if we are asked to find the new length after it has been applied on a body, we make use of this formula to find our new length. And if we are asked to find the expansion, which is change in length, we make use of this formula. So we have all those formulas to solve the problem tonight. Okay, we can as well look at their values here. Alpha represents linear expansivity. L1 is original length before the application of it. L2 is increase in length after application of it. So the L2 is new length after the application of it, while delta L is increase in length, or you call it expansion or change in length, and delta theta is change in temperature, as the case may be. Also, we have something similar when body expanded in 2 dimensions. We call it area expansivity, or you can as well call it superficial expansivity. The symbol for this is beta. You can see the symbol there, and the formula is also very similar to the linear expansivity formula. The only difference between them is that in this case we are dealing with area, so new area minus the original area divided by new area multiplied by change in temperature will give us superficial expansivity, or you call it area expansivity. And this formula is what we have here as well, because A2 minus A1 equal to delta A. That is what we have there, as you can see. Okay, and we also make our A2 the subject of the formula, also our delta to be the subject of the formula from this equation, and we have those. And also there's something you need to consider here. First part, we talk about linear expansivity. Here we are talking about area expansivity. They have a relationship. Area expansivity beta is twice the linear expansivity of a material, so that's why we have beta equal to 2 alpha. Okay, similarly we have something similar in when the body is expanded in 3 dimensions. We call it volume or cubic expansivity. It is represented with a symbol gamma. So gamma equal to V2 minus V1 over V1 into delta theta, and that is what we have here. Also we make V2 the subject of the formula, as well as delta V the subject of the formula. And also this gamma, which is cubic expansivity, is 3 times the linear expansivity, as you can see here. That is, the implication of this is that when linear expansivity is given and we need to use cubic expansivity, we can multiply our linear expansivity by 3 to have our cubic expansivity. So also when linear expansivity is given and we need superficial expansivity, we multiply by 2 to have our superficial expansivity. Okay, from here I think we can quickly consider few examples before we move on. Okay, let's quickly switch to another page where we can have our examples. Okay, here we have okay, let's wait for this one to come up. Okay, sorry, just a minute. Okay, you can see from our example 1, the question says a wire 20 meters long is heated from 5 degrees Celsius to 55 degrees Celsius, and if the change in length is 0.02 meter, we have to calculate the linear expansivity. First thing that we need to do here is to write out the given parameter. first thing that we have in the question is we have a wire 20 meter long, that is original length, our L1 equal to 20 meter, and it's heated from initial temperature, which you can represent with our theta 1, which is 5 degrees Celsius, to the final temperature, which is 55 degrees Celsius. You will agree with me that a change in temperature will be equal to 55 minus 5, and that is 50 degrees Celsius. Okay, and if the change in length is equal to 0.02, what is our change in length? The symbol for that, delta L equal to 0.02 meter. We are asked to find the linear expansivity. And what is the formula for linear expansivity? We have that to be equal to, that one is alpha, which is equal to change in length according to what we discussed earlier over original length multiplied by change in temperature. And with that, we can see our linear expansivity equal to change in length, which is 0.02 divided by our original length according to the equation is 20 multiplied by change in temperature, which we calculated to be 50. And with this, our linear expansivity, if we press our calculator very well, will be equal to 2 multiplied by 10 raised to the power minus 5, and the unit for linear expansivity is per Kelvin. So this will be our answer to this question. Let me quickly go through it again. From the question, we have a wire of length 20 meter, that's original length, and it's heated from temperature of theta 1 to theta 2. Theta 1 is 5 degrees Celsius, while theta 2 is 55, and so we find our change in temperature to be 50. And when this happened, it caused an expansion of 0.02 meter in this wire, and that is what we have here. We are now asked to find linear expansivity, and formula for linear expansivity is what we have right here. That is what we have right here. Okay, using that formula, substituting our parameters into the formula, we have this answer, which is 2 multiplied by 10 to the minus 5 per Kelvin. That is our first example. Let's consider another example. This one is talking about area expansivity. That is when an object expands in 2 dimensions. Now the question says an aluminum plate has a surface area of 1.5 square meter. That is surface area, original area equal to 1.5 meters square. That's the meaning of our square meter. When the temperature, initial temperature, equal to 20 degrees Celsius. Now they now ask us what will be the surface area, that is the new length, the new area, when the temperature is reduced. When the temperature, that is theta 2, is now minus 30 degrees Celsius. So the temperature here reduces, and what we expect to see here will be contraction instead of expansion, because the temperature reduces. Okay, now we still go with the same approach from what we've discussed earlier during the introductory part of this lecture. We will realize that we can make it to the subject of the formula let's see if we have superficial expansivity equal to A2 minus A1 over A1 change in temperature. We can make A2 the surrogate of the formula, and doing that we will have our A2 to be equal to A1 into bracket 1 plus beta delta theta, that is value of our A2. And substituting all the values into this equation, because we have them already, only A2 is what we are looking for. We can have our A2 to be equal to, our A1 is 1.5 according to the question. 1 plus, okay, let's open a bracket for this. Beta, okay, I think we quickly need to have what our beta is. Remember that our beta equal to 2 alpha, and in the question we're given alpha, so when you multiply the alpha given in the question by 2, let me see, we have a 2 multiplied by the alpha given in the question, which is 2.5 multiplied by 10 raised to the power minus 5, and that's multiplied by our change in temperature. Remember, our change in temperature is from 20 to minus 30, so we have minus 30 minus 20, that is theta 2 minus theta 1. So you can press all this on your calculator, or you do it one after the other, and in doing that we are going to have the value of our A2 to be equal to, if you press your calculator, you can do it one after the other, or you press it once using the bracket where it is necessary. So we are going to have this value as our new area. The original area is 1.5 meters squared, while the new area is 1.496 meters squared. So we experienced little contraction, little reduction in size of the aluminum plate. Okay, let's check another example that has to do with volume expansivity. Now in this particular one, we have a solid material of volume 100 centimeter cube, that is here V1 equal to 100 centimeter cube. That's the meaning of cube, that's the meaning of a cube centimeter. This one is heated through a temperature of 40 Kelvin. When we are in a question like this, when we come across heated through a temperature of 40 Kelvin, what this is telling us is that our change in temperature for this question equal to 40 Kelvin. So in this particular question, we are not having theta 1 and theta 2 separately. They've calculated delta theta for us, that is theta 2 minus theta 1 already. And most times some students will ask, do they need to change Kelvin to Celsius or whatever? You don't need to change it, because we are dealing with change in temperature here, not the actual value of each of the temperature. Okay, now we have to calculate the increase in volume, that is volume V2. Sorry, we have to calculate the increase in volume, which is delta V. That's change in volume. That is what we are looking for of the material, and the linear expansivity alpha of this material is given as the following in the question here, that is 2 times 10, and this will be raised to power minus 6 per Kelvin if you take it to standard form. And we all know that gamma, which is cubic expansivity, equal to 3 alpha. So if you do that on your calculator, 3 alpha will be equal to 3 multiplied by the value of alpha will be equal to 6 multiplied by 10 raised to power minus 6 per Kelvin. And having that, we can now substitute into the equation, making delta V the subject of the formula. Delta V, from the introductory part of the question, we've seen that delta V will be equal to gamma V1 delta theta, and this makes us to have our delta V to be equal to, our gamma is 6 multiplied by 10 raised to power minus 6, and our V1 according to the equation is 100, and our delta theta equal to 40. So delta V will be equal to 0.024 centimeter cube. So that is what we have. Let me quickly summarize, or let me run through this. In the question, we have the original volume of a solid as 100 centimeter cube, and when it is applied, the solid experiences a change in temperature of 40 Kelvin according to the question. Okay, and we are asked to calculate the increase in volume, which is delta V, and the linear expansivity, which is alpha, is given in the question. So putting all those ones into consideration, we first listed out all the parameters, and we find the value of our gamma, gamma equal to 3 alpha, and that is what is giving us this. Okay, so moving away from that, we substituted the value into this formula. From the introductory part of this class, I've talked about this, making delta V the subject of the formula. We have this one, and substituting all our values into this formula, we arrive at 0.024 centimeter cube as the increase in volume. Let's check one more example, but before doing that, if you are on watching this and you are yet to subscribe to this channel, please do, so that you get the notification whenever the class is on. And also remember to click a notification button, and whenever you watch this class and it's adding any value to you, kindly give me a thumbs up. And if you watch this and you have any question, just drop your question in the comment section. The question will be attended to. Okay, now let's look at the last example that we'll be considering tonight. The question here says the ratio of a linear expansivity of 2 metals P and Q equals to 3:5. That is linear expansivity of P and Q, they are in the ratio of 3 and 5. When heated through the same temperature change, the ratio of their increase in length is 1:2. We have to determine the ratio of their original length. This question is a UTME question 2007. Okay, let's just list out what we have in this question. They said the ratio of linear expansivity of P to Q. Let's just say linear expansivity of P is this ratio linear expansivity of Q, and that is given as a 3:5. When they are heated through the same temperature change, that is the same temperature change is what they experience, that is their delta theta P equal to delta theta Q, delta theta Q. Okay, now when they are heated through the same temperature change, they experience increase in length, that is delta L for P ratio delta L for Q equal to 1:2. So we have to determine the ratio of the original length, that is we have to find Fp ratio LQ. That's what we are looking for in this question. Okay, very good. Now let's quickly look at something here. From the question, we were meant to know that both pass through the same temperature change. If you make this temperature change in temperature the result of the formula, that is a change in temperature, result of the formula and the equation of linear expansivity, you have delta L over L1 alpha. And if delta theta P equal to delta theta Q, we can easily say that LP, that is change in length of P, over LP alpha P, that is linear expansivity of P, equal to delta LQ over LQ alpha Q. What is just happening here is that from here we have the formula for change in temperature, and the change in temperature for both P and Q are the same. We just pick this for P and Q and equate them to each other. That is what we are having right here. Okay, now let's move on to see how to substitute the value given in the equation. Remember, the ratio of delta LP to delta LQ is 1:2, so we can easily say 1 over, let's say 2 over, because this to this is 1:2, and the ratio of LP to LQ is what we are looking for, so just put LP there. Okay, just put LP there, and LQ, we are looking for the two of them, and the ratio of alpha P and alpha Q according to the equation is 3:5. Let's just insert their value. So here we have 3 and here we have 5, right? Okay, let's see how we can play around this. From here we can cross multiply, and that gives us 6 LP equal to 5 LQ. And remember, we are looking for the ratio of LP to LQ, so we can say LP over LQ equal to, that is this is coming under this, definitely this will go under this, so we can say that is equal to 5/6. And from here we can say LP ratio LQ equal to 5:6, and that gives us the final answer to that particular question. So please, if you have any question, feel free to drop your question at the comment section, and the question will be attended to. And if this class has helped you one way or the other, please feel free to share the link with your contacts, share with your friends, let them join the class. And the class will be coming up at least 3 times in a week. And in the next class, we are going to consider a topic in mathematics by the special grace of God, and that will be coming up on Friday. We are going to consider a topic in mathematics. Please, whenever you join this class and you enjoy the class, please feel free to subscribe to the channel and give the class a thumbs up. Thanks for watching.